All right, so today is just pretty similar to last time, except just with multi-qubit Hamiltonians. So it's VQE again, Variational Quantum Eigensolver, which the basics were discussed last time. And it's just, last time we dealt with 2x2 matrices, i.e. single qubit Hamiltonians. But today we'll be talking about 2-qubit Hamiltonians. So 2-qubit Hamiltonians. And yes, I said previously that I had all of this written out, and I did. However, I was looking to expand it more into maybe larger Hamiltonians, but I had trouble doing that, and I'll explain why when we get to the code. So first off, there's going to be two parts. First, we're going to do a simple matrix, and then we're going to actually simulate some real, I guess, real-ish atoms. And you'll see a common, if you've ever taken chemistry, or I guess this also comes up in physics when you talk about the hydrogen atom and stuff, you'll see a lot of curves of energy versus bond length for hydrogen. So if you have a little hydrogen atom, right, or a hydrogen molecule, and you have the length of bond, you'll see it goes something like, that's a really bad graph, but basically we're seeing that if the bond is really short, it has too much energy, and that's not good because the nucleus of the two atoms is too close together, so there's that electromagnetic repulsion, and then as you get further and further apart, there's the counteracting forces basically, and so we can see that right here. This is sort of the nice normal minimum in this area. So it's a bad graph, but you'll see what I mean when we get there. So first, let's the matrix that we're going to be specifically talking about for this example is the following 4x4 matrix: 1, 1, 0, 0, 1, negative 1, 0, 0, 0, 0, negative 1, negative 1, 0, 0, 1, 1, 1. So now the key, if we have this matrix, how do we break it down into its component Pauli matrices? How do we represent this as Pauli matrices? And so this is I guess there's probably a lot of algorithms for Hamiltonian decomposition, but I built this from the Pauli gates up onto this, so I can just immediately tell you that we can reduce this down. We can say that this is equal to 0, 1, 0, 0, 1, 0, 0, 0. So this plus 1, 2, 1, 1, 1, 0. They're not the most well-drawn matrices, but this is what it equals to. And so from here, remember that when we have two qubits going along here, and if we just have an X gate and maybe a Y gate, this is the same as doing this. And this is the, there's different names. Some people call it Tensor Products. Some people call it Kronecker product. I think Tensor Products is more specific or something. I don't know the details of the name, but I'm just going to call it Kronecker. I don't know who he was, that guy, but he also made the Kronecker delta function. So pretty prolific mathematician, I guess. So when we look at that, all we have to do for to find this product is basically we just you'll see this oftentimes if you have something like, you'll represent it differently. This will be so it's sort of an element wise multiplication of matrices. So you'll take this matrix and sort of multiply it by each element. So if we do, for example, let's try and generate this first one here. So we can see that this this first matrix is equal to, you might be able to guess this just by looking at it, but it's equal to x and z, or poly x and poly z. So if we do it out, we can see, oh, I just realized I'm not writing. So if we do it out, we can see that, if we do, now let's do this first matrix. We can see that if we do z Kronecker x, we get we see that we have, remember z is 1 0 0 negative 1, so we have 1 x 0 x 1 x negative 1 x. So this equals x 0 0 negative x, which you can see since x is 1 0 1 1 0, which can be seen this component right here. We can see that this is clearly true. The second one, you can probably guess that's just, I'm not going to do it out, but that's just ZZ. And so now that we have this matrix, we also have the decomposition. There's no constant added. There's no multiplication factors. There could be. I didn't feel like adding them though. So we can see that this Hamiltonian is equal to ZX plus Z, which can also, you might see it written sometimes, Z0x1. So Z on qubit 1, Z on qubit, 0, X on qubit 1 plus Z0, Z1. You'll see this a lot more probably in literature, because if you have a ton of these, maybe you have like 8 qubits, like you don't want to do all those tensor products or Kronecker products. And so you'll see these indices a lot more. So now that's pretty clear. This is a simple, straightforward example. We covered a lot of things in the last discussion. So now we can just go over, I bring up this recording software, and we can go over and we can look at the code to do this. There we go. Okay, so oh, I guess one thing before I go over I should talk about is when we apply, so if we're doing these operations on single qubits, right, we want to convert x into the measurement z basis. So we did rotations of pi over 2, and we want to convert y to z. However, you might think, for example, with the zz part of the Hamiltonian, well, we can just measure those two. However, that is actually, we can see, if you look at zz, you might think just measuring z. However, converting z to z, this is the measurement that you're doing. It's important to note that this Pauli measurement, this is the Pauli measurement, has an associated unitary transform. And so if we want to do this, if we want to measure z, what we have to do is we first have to apply a C0 gate to them. And if we want to do, as previously mentioned, zx, then we have to apply we have to do C0 and then identity matrix. So basically what this means is we have to apply a Hadamard gate to the x and then apply C0. And so this is where, I guess calculating all of these unitary transforms for higher order Pauli measurements, I'll admit I didn't look that much for it, but I don't know exactly the best way to compute these. And so, if you have z, y, x, z, I don't know what the associated unitary transform is. I'm sure it's out there. I just didn't find it, but I did look a little bit, and I do not know the best way to do that. So that's something I should probably learn though. And so now that we know the associated unitary transforms, let me just say, once again, this is kind of a trivial matrix to solve. We can just analytically see that I mean, I just plugged this into a calculator. To be honest, we could see that as 2 eigenvalues equals plus or minus the square root of 2, which is something like plus or minus negative 1.442 something. I don't remember the exact value. And so that's once again, we can just analytically solve this. And so we can see now, with that information out of the way, we can see that we can go back to the code. And it should hopefully make sense now. So we have this creating the circuit here. This time I have 2 parameters. In front of each qubit, I just do Rx and Ry. And here we can see that I make it once again as a single circuit because it's feasible to do so with just, it's a 2-qubit Hamiltonian repeated twice. So it's just 4 qubits, which is pretty trivial to do. So qubit 0 is 0 and 1 are the Z Kronecker X, and qubits 2 and 3 are ZZ. And so here we can see that first we apply the Hadamard gate to the X, and then we apply C0. And so this is for Z Kronecker X, and this is for the ZZ operation. This is a C0 right here that's for. The Hamiltonian is the same, constant, measuring in the Z bases. It's important to note that you just add them, so you're just measuring the Z bases as usual and just adding them. So we create the 4 qubits, the 2 parameters, we create the circuit, the Hamiltonian is a sum. This is all pretty much exactly the same in terms of code. All that's different is this stuff up here. And then we have the input, standard data type of string, VQE circuit, readout operator. There we create the model, and I don't even compile it or try to use gradient descent because it just takes so much longer. We use the standard, my little hacky function. I don't know if that's the best way to do that for using the SciPy minimize function. So here we have minimize, and we're using Nelder-Mead once again. And so we can simply run the code. Oh, there we go. I do not know what was happening right there. The screen is all messed up. There we go. Okay. So, yes. So now we can do. So if we run the code, it will we'll see the circuit momentarily, and then we will see. Yeah. So here's what we can see. We can see that the readout operator is all in the Z basis. We can see this is the X part. We have the Hadamard gate, and then ZZ. And so we can see right down here, ignoring the simplex because it's Nelder-Mead is just a simplex-based algorithm. I don't really know why that matters. We can see that it terminated successfully at negative 1.44, which is pretty much exactly negative square root of 2. And so that's the goal. It looks like the Rx actually didn't have a huge impact. We can see that this it's very close to 0. So I don't know, maybe we could try taking it out. Let's just go over. I'll actually just take out the Rx parameter, and we'll see. Let's see actually just what happens. I don't know what's going to happen here. And this is actually a good discussion because we do want to minimize the number of parameters that we have to optimize. That makes this whole process easier. Oh, whoopsies. I also have to change the input into the. So there we go. Let's see. I imagine it'll be pretty similar because once again, it's a pretty simple circuit. Let's wait for that. There we go. Yeah, pretty much found the exact same point. So that doesn't really matter, but that's just interesting to note, something to consider for optimization. Now, let's go back to the forward, so to speak. And I want to briefly mention the paper that this is based on. It's called, oh, do I really want to write this out? No, I do not. I'm just going to put the name. It's by O'Malley, and it's 2017. And I'll link it as always. And it's called Scalable Quantum Simulation of Molecular Energies, is what it's called. And so, and there's an associated blog post that I will also link that does this whole thing even more from scratch. So I recommend that. So basically, they present, okay, they have a molecular Hamiltonian for hydrogen that can be written in the following form. Constants Yeah, I'm just writing it out. It's pretty long. So here we have it. We can see that this in total is, that's a constant. So it's 1, 2, 3, 4, 5 terms. Well, 6 terms if the constant is included. And then we can see that this is something we can do on a single circuit because this is 1, 2, this right here is 2, 4, 6. There's a total of 8 qubits necessary for this simulation, and it's sort of broken down into little two qubit boxes, I guess. And so and so what we're trying to do is we're trying to say we'll change these constants to reflect the Hamiltonian of the hydrogen atom at a certain length, and then we will calculate the energy at that bond length. And so the ground state energy, which is really all we care about. And so if we look at this, they just give the constants in the appendix in the paper. And so I just copy them from there. But one thing to note is that they have a specific outline for how they do the paper, which is different than, conveniently different than most things. Normally, I always write, this is qubit 0, this is qubit 1. So we go out, they do it the other way around. This is qubit 0, this is qubit 1. So don't get too confused. But the specific circuit that they have is, I'll do my best to draw it, they have an X gate here, and then they do Rx pi over 2, Ry pi over 2, and then they have a C0 gate, and then they only have one parameter. That's an RZ right here. That's the one parameter. And they do another C0 gate, and then they have Ry negative pi over 2, Rx pi over 2, and then they have the measurements out here. And so the exact rationale behind this circuit stems partially from a theoretical rationale, but also because they actually implemented this on hardware, and so you're constrained. Hardware people do their own thing, and so if this is what they can implement on hardware, this is what they implement on hardware. And so that explains why the circuit is so complicated. Now, let's get into the code. So first, let me go over that. There we go. And so what we see is standard imports as always, the same function. So now we want to create, because this is 8 qubits, once again, I do this on one circuit. So this is where, this is just for looping over each of them. So for each sort of mini circuit that I simulate in one circuit, first we apply X to the, I just refer to them as down and up because 0 and 1 gets confusing when I'm used to the other way. So we do the X on the bottom circuit, and we rotate Y on the top, rotate X on the bottom, and then we can do the C0 gate, controlled by the up on the down, and then here's the one parameter. the RZ gate, then we do another C0 gate, then we do RY and RX. And so this is the circuit as described in the paper. And now we have to do all of these unitary transforms to be able to measure them. And so the first one that we have is Z or 0 or identity tensor Z, which is you just apply a swap gate. The second one is Z tensor identity, which you don't have to apply any gate. That's why you don't see anything on 2, 3. And then the next one is the ZZ, which is just the C0 gate. And then the next one is the, maybe I should actually write these down. That might, rather than me just saying them. If we have, so if we have the term ZI, that's just nothing. We can just measure that. We have I, Z, we do swap. If we have, the next one is ZZ, then we do ZZ, then we can do C0. If we have YY, which is the next one, then we have to do C0. This is C0. Doing and then X is another, a lot of C0s you'll see. And so specifically one thing to note here, once again, there's a big table I found for 2-qubit unitaries. That's how these are easy. I don't have a table for bigger ones, so that might be something to find. One thing to note is that this is equivalent to 1 negative I, 0, 0, whereas normal S is the 1I because that's just a complex conjugate. And so to recreate this, you can just do that's equivalent to, that's equal. And so that's why you'll see the Z gate. So now we can get back over to the actual document. Yes, so we do ZS here for that, and then we apply Hadamard to each. So this is basically HS dagger, and then we have the C0 for the double Y's, and then apply H's for the X's, and do C0s on those. And keep in mind here, you'll notice there's actually 10 qubits in this simulation, not 8. And that's because the circuit that they describe in the paper is actually 2 qubits per term in the Hamiltonian. So even 2-qubit Hamiltonians, even if they have nothing in the second part of it, even if it's just the Z, it's important to note that is, if you're adding matrices together, you can't add a 4x4 plus a 2x2. That isn't possible. So you have to make them all 4x4 matrices. That's why you'll notice even when there's a single qubit term, even if we're just caring about Z0, that it still matters to the to have this 2-qubit term, or 2 qubits for that term. So then we have the Hamiltonian, which once again we're measuring all in Z's. And then we have, these are just coefficients. Some of them, they have a whole table. I copied them by hand, so I didn't want to do all of them. This is just a list of the different G's, or these terms in the Hamiltonian. And then these are the distances, the bond lengths. Specifically, this is the distances in angstroms. And so we can see 0.2 to 0.25. The actual bond length is something like 0.65, 0.7. I don't remember. Maybe a chemist knows that. And so then each time we can do okay, it has finished running, and I will let me bring up the little graph that it showed. Okay, there we go. So we can see that graph. It's a little off. It's not perfect, but keep in mind this is this is guaranteed to be above the values of the appropriate values. So that is why it looks a little off, because it's not quite the exact minima of every point, and so that is worth noting. But you can see, if I here, let me get the figure from the paper up here. If I just bring up the figure, let's see if I can move this over and then also share this. There we go. We can see, this isn't as big, maybe make that bigger. We can see this is what the figure looks like. You can see the curve down here isn't as sharply defined, but you'll notice that pretty much every point is slightly higher on my graph, but the gist is there, and for pretty simple sort of points, it makes sense. Also keep in mind, I do not copy all, they have a lot of points, and so it's a rough approximation. You can see there's little lines that are jagged in this area, and so but it looks pretty good, all things considered. And so that's pretty much it in terms of the VQE two-part series, I guess. And so you can see the entire paper to replicate. Basically, I'm excluding these lines because they could be one line, is well under 100 lines. If I exclude these, that's like 40 lines right there. It's basically 60 lines of code, which is nothing. And this is even less. This is just 40 lines. So you can see VQE and TensorFlow-Quantum very easy. Replicated a paper, and I'll link it below.